Okay, so people, welcome in the next edition of VGS IT. This is the Vision, Graphics and Speech Invited Talks at the Faculty of Information Technology. And I'm glad that we are physically restarting after a long time. Before I present the speaker, big thanks to the Student Union, because you know that during this winter term the faculty is pretty much 110% booked. So this was the only available space, and the Student Union was kind to offer it to us, including a very skilled technical support. So thanks a lot, our colleague at the audiovisual equipment. We have also the streaming, and the talk will be recorded. And it's my pleasure to welcome Tanel Alumäe from Tallinn, from Estonia. So Tanel has a PhD from Taltech, from the Tallinn University of Technology, and he worked in many friendly labs that we know well. So in LIMSI, CMRS at the Aalto University, and also at Raytheon VBM Technologies, and he's basically a speech guy focusing on low resources, and that's what his talk will be about today. So the floor is yours, Tanel, and thanks a lot for accepting to speak here.
Yeah, thank you. This is a really great honor for me, because the speech technologies group in BUT is definitely one of the top groups in the world. So for me, it's a really great honor. First, a few words about my university. So Tallinn University of Technology, or Taltech now, as it's now called, is a modern research-based university offering bachelor, master's and doctorate degrees, and mainly technology fields, but also business. It has nearly 10,000 students, approximately 16% from them are abroad, which is the largest percentage among the universities in Estonia. Some of the flagship research directions in the university are considered to be health technologies, smart city, applying various technologies in industries, and valorization of natural resources. The Laboratory of Language Technology in the university is part of the Department of Software Science. Our main research directions are various fields of speech processing, but also phonetics and collection of speech corpora. And we also focus a lot on developing accurate and usable Estonian speech processing technologies for both end users as well as industry partners. The lab has 3 senior researchers and 4 PhD students, and we offer 2 master level courses. So a few words about me. As Onsa said, I got my PhD from the same university. That was already in 2006, and I did some postdocs in different institutions. Currently, I'm the head of the Laboratory of Language Technology in Taltech, and my main research interests are different fields of speech processing with a focus on practical approaches to low-resource scenarios, such as how to do transfer learning smartly, how to do weak supervision to generate labeled data automatically, and so on. So my talk will concentrate on weekly supervised training. First I will say a few words about weekly supervised training in general, and then I will concentrate on 2 cases where weak supervision can be applied in speech processing. One is in speaker recognition, and the other is in language recognition. So there are different kinds of so-called supervision in machine learning. The classical case is the fully supervised case. This is the case where you have a bunch of training samples, and all of them are labeled typically by human annotators. And the goal is to train a model for predicting the labels for unseen data. In the supervised case, you just have a bunch of training data samples, but you don't have the labels, and typically the goal is to find some kind of structure, for example, some kind of clusters in the data. And this semi-supervised case, which is actually probably the most popular research direction today in machine learning, considers the case where you have some labeled data, but typically a lot of unlabeled data. And the model, the goal is to train a model that can predict the labels, but also at the same time make use of this additional unlabeled data so that the model will be smarter. Then there is also weakly supervised and distantly supervised learning. And sometimes they mean the same thing, sometimes they mean different things. Typically, weakly supervised training handles the case where full data labeling would be very costly. But there is some way to generate labels automatically and very cheaply from some kind of external source. And there are many different types of weak supervision. Some of them are given here. A typical case is candidate labels. So in this case, each training sample is assigned not the correct label, but many labels, and only one of them is known to be correct. Probabilistic labels is kind of similar, but in addition to the candidate labels, you would also have a probability for each of those candidate labels. Then a very popular case is this crowd annotation, where the labeling, data labeling is not done by experts, but some crowd annotators, typically non-experts, and they generate labels that have lower quality, so you know that their labels have some noise. Then weakly supervised training can also consider cases of label constraints and label proportions. So label proportions, for example, handles the case where you know the proportions of the labels in a set of instances. You have a set of training samples, and you know that, let's say, 25% of them are of class A, but you don't know which ones precisely correspond to each label. Okay, so let's start with speaker recognition, and let's first consider the case of supervised training. Most of you are experts in this field, so I won't stop on it for very long. So training speaker identification models typically requires hand-segmented training data. So if we want to train speaker recognition models for John and Mary, then we need to have training data for John and Mary. So, and this needs to be accurately time segmented. So we need to know, we have to have those training speech recordings, and we need to have those accurate time and end markers for John and Mary where they exactly speak. And of course, producing such data is costly, especially in the case where we want to cover a very wide range of speakers. For example, thousands of politicians for media monitoring purposes, or perhaps a wide range of celebrities. And of course, it's also difficult to keep such models up to date and enroll new speakers and so on. So weakly supervised training that I'm talking about today requires only recording level labels. So we have to have this recordings, speech recordings, and for each recording we only need to know the set of speakers who at some point speak in each of those recordings. And time-based annotation is not required. And producing such data is, of course, much easier, and often such labeling can be generated automatically from some kind of metadata. So how does this weekly supervised training work? So this is the rough outline of this method. I will stop in most of those steps in more detail, but the main idea is that we start with audio files and the corresponding speaker labels, so a set of speakers for each audio file. Then we do speaker diarization, extraction of embeddings. So on my pictures here I have I-vector extraction, but it doesn't have to be I-vectors. It can be any speaker embedding paradigm like X-vectors or ResNet or whatever is used nowadays. Then based on this, we do this weekly supervised DNN training, which is the kind of the main step of this method. As a result, we get the DNN that maps speaker embeddings to speaker IDs, which can be used for relabeling the training data, and the result is a data set with time-segmented speaker labels. And this can be used for training a speaker recognition model with any speaker, well, with any method which you want to use, like X vectors plus LDA, PLDA, or something like this. Okay, so in more detail, the training data is a bunch of audio files. And for each audio file, we need to have annotation, which is basically just a set of speakers who occur there. We only need to annotate those speakers who interest us, so-called persons of interest. The recordings can contain speech from other speakers who do not interest us, and we don't have to label them. It is important that we have several audio files from each person of interest. The more the better. And it's also important that no two speakers only occur in the same files. So if there are two speakers who only occur in the same files and never anywhere else, then of course we don't have any way to distinguish them or sort of break the tie. So we start the process with speaker diarization, so we can use any speaker diarization system, so something off the shelf. So speaker diarization basically discovers automatically speaker turns in the long speech recordings and clusters the resulting turns according to the probable speaker identities. So if this is the input speech recording, then we get something like this from the speaker diarization step. So, and after the speaker diarization step, we compute the embeddings for each of the resulting clusters. Again, we can use an off-the-shelf model for computing the embeddings. It can be trained on some external data. We have to have something. It can be I-vectors or X-vectors. I think in our experiments we used I-vectors because this was a few years ago. So basically most of you know this very well, but the idea is that the input is a variable length speech utterance, and you map it to a fixed size vector, and the idea is that similar utterances, meaning those that originate from the same speaker, have similar embeddings. And also we average the embeddings from the utterances of the same speaker. So if the speaker diarization step gave us this information, so such segments, then we, in order to compute the embedding for speaker A, we average the embeddings from this segment and this segment. And for speaker B, this and this segment, okay? Finally, we come to the main step, training the DNN that maps embeddings to persons. So the training data for this DNN is a bunch of recordings, each of which consists of a set of persons that we know occur in this recording, and a set of embeddings. However, of course, we don't know which embedding corresponds to which speaker. Also, the number of embeddings can be, and usually is, different from the number of speakers in our label set, because there can be other speakers speaking there in the recording. So how to train such DNN? So this is the outline of the algorithm. I know that reading this algorithm is from a slide is not very convenient, so don't worry if you don't understand it now, but the main idea is that we take all the recordings, we shuffle them, and then we go over the recordings one by one. For each recording, we take the DNN and compute the posterior probabilities for all the embeddings that were discovered in the speaker diarization step. Then we average the predictions or the posterior probabilities over one recording. Then we compute the expected average or the ground truth average. And the ground truth average is 1 over the number of embeddings for persons who are supposed to occur in this recording. It is 0 for all other speakers, and for this unknown speaker, so this model has a special output that models unknown speakers or sort of a background speaker. For this unknown model, unknown speaker, this expected average posterior probability is given with this expression. Then we compute the KL divergence between the predicted average posterior probability and the expected posterior probability, and we compute the gradients and update the model. And we do this until convergence. Okay, so why such kind of expected average posterior probability? So let's say that the recording has 5 embeddings. So the speaker diarization step discovered 5 speaker clusters. And for this recording, our label set contains 2 speakers, John and Mary. So the number of detected speakers is 5. So for John and Mary, the expected average posterior probability is 1 over 5, because we know that one of those embeddings has to correspond to John and one to Mary. For other speakers, so the rest of the persons of interest, the expected average posterior should be 0. So we know that they do not speak in this recording. And for this unknown speaker model sort of absorbs the rest of the embeddings. So it can be still confusing, so let's look at it graphically. So let's say we have a recording with with 3 discovered speaker clusters. We compute the embeddings for them. We feed the embeddings through the DNN, and the DNN gives us the posterior probability for each of the speakers in our all the training data. So let's say that those speakers are A, B, C, and D. Let's say we have 4 persons of interest, and the unknown speaker. And then we just average the posterior probabilities over the speakers, over all the embeddings of this recording. And we get something like this. So the label for this recording contains speakers A and C. So we know that A and C speak in this recording. So we compute the ground truth average. We know that, so for A and C, because they do occur in this recording, the average posterior should be 1/5. No, 1/3, because there are 3 embeddings, and for unknown speaker it's also 1/3. So now we compute the difference, or the KL divergence, between the predicted average posterior and the ground truth average posterior, and we backpropagate. So what does this backpropagation tell the model? So it basically tells the DNN to modify its weight so that next time it sees those embeddings, it should output a larger average posterior probability for speaker A, a smaller average posterior probability for speaker B, because for B the average posterior now is something pretty big, but we want it to be 0, because B is known not to speak in this recording. Okay? So let's say that now we have trained this DNN for a while, and the DNN has learned that, that this first embedding corresponds to speaker A. So it outputs a large posterior for speaker A for this embedding, and a very small posterior for speaker A for the rest of the embeddings. We still compute the average, we compute the ground truth average, which is the same as in the last slide. We compute the difference, or the KL divergence, and backpropagate. And now the backpropagation step basically tells the model not to do anything about speaker A. So it tells us that you are doing fine with speaker A, don't worry about this. So basically this training method never tries to find explicit correspondence between embeddings and speakers. It only deals with averages. But because it only tells the model to assign a non-zero average probability in the case where the speaker is speaking in this recording, it turns out that the only way to satisfy this condition for the model is to actually learn the exact correspondence between embeddings and speakers, given that our data quality is good, so the different speakers occur in many different recordings. Okay?
So can I ask you, Tanel, can you have this reordering problem that basically you don't know which of the speakers on the left corresponds to which of the reference speakers, or is it clear, is it basically given by this diarization / speaker identification model? Because, I mean, for example, when she works with the speaker separation, the reordering or the permutation is a common problem.
Yes, yes.
Is it a problem for you or not?
No.
You have the identity basically, right?
This reordering problem is not even sort of valid for this kind of method.
Okay. And there is another question from Ganesh. Do you do something to help symmetry grading, e.g. in batch construction?
No. So we haven't really. I will talk about this later. That it's important to have each speaker occurring in many different recordings, and if this is true, then the model learns. If the speaker occurs only in a few recordings, then the model does not necessarily learn a good way to predict his or her identity from data. So the DNN that I have been talking about, this one, what kind of DNN it is? So it turns out that it can be very simple. We just used a DNN with 2 hidden layers and with some dropout. Okay? So once we have the DNN trained, we can use it to relabel our training data. So the embeddings discovered by the speaker diarization step in the training data, and this way we can actually relabel our training data with accurate time level annotations, and because we can see which embeddings correspond to which time segments in the training data, we can map back the identities from embeddings to the segments. And this way we get actually time annotated training data. And then we can use any speaker recognition method to train our speaker recognition system, okay? So let's come to experiments. The first experiment was done using the Voxel App Data Set. So I'm sure most of you are familiar with Voxel App. It's very popular in speaker recognition community. It's basically a data set of about 7,000 celebrities, which is collected by searching YouTube using the term celebrity name plus interview. And it is assumed that if you use this term, you get mostly videos where this celebrity is speaking. And this Voxel App data set actually consists of segmented speech data from those videos, and it's constructed in a very smart way by using face tracking, active speaker verification, and face verification. So basically, face tracking is used to find out video segments where this certain celebrity is speaking and where his lips is in sync with the audio, and it is assumed that in those video sections this certain celebrity is actually speaking, and the speech in the video corresponds to his or her identity. So this is how these official annotations for Voxel App were constructed. So we used our method to produce alternative segmentation for the Voxel App dataset. So we didn't use the official segmentations, but we actually used the raw audio from those Voxel App source videos. And we used this weakly supervised method to relabel this raw data. So assuming that the annotation for each of the video contains only this celebrity. Actually, it turns out that some of the videos in the Voxel App data correspond to correspond to 2 celebrities. I guess those are the videos that have titled something like interview with Bill Gates and Elon Musk or something like this. And we used this weakly supervised training to train a DNN that maps embeddings to celebrities, and then we use this to relabel the the original raw data, and it turns out that this method gives us 3 times more labeled segments than the official Face ID based method. Which is, so in the official segmentation we have almost 3,000 hours of data, and our method gives us almost 10,000 hours of data. Why is this good? This is good because X vectors or any other DNN-based speaker embedding method is known to be very data hungry. So the more data you have, the better embeddings you get. So since our method gives us more segments, does it also improve the resulting X vectors? It turns out that yes, it does. If we use the reference annotations of Voxel App, then we get something like this on the Voxel App 1 test set. And if we use our annotations, we get a lower equal error rate than the DCF scores. We also experimented with a voices dataset, which contains speech in reverberant conditions, and also on this dataset, equal error rate has a nice drop when using our segmentations. Okay? Yes, it was done. I think it was actually done 3 years ago, and then it it was pretty good. But I know that nowadays it's like one.
But that's not a problem. I would have a question. Would you be able to share such a segmentation?
Yes.
Because like, there are systems that would have like slightly below 1% equal error rate, and it would be, let's say, for us to try your segmentation if a larger network and more training can squeeze still more out of the data.
Yes, absolutely. So I have the segmentation somewhere on GitHub. The problem is that you then also have to re-download the YouTube data because I only have the segmentation, not the audio.
Yeah, because they already, what they published was just a cutout segments and the YouTube IDs, but we would have to download the data.
Yes, but if there is a large interest, then I can actually take care of the data downloading also. I know that YouTube has gotten recently much more strict about this kind of method, so I'm not sure if it works, but we can look at it.
Okay, we can maybe talk after.
Yeah.
So I have another question. Basically, you said that you covered 96% of the original segment, which can be considered as basic precision, maybe.
Yes.
But how about the recall? So how precise did you measure on some maybe no doubt set? How good the segments that are automatically determined are? Or
we didn't really measure recall on this data set.
Okay,
so the second experiment with this method was done using Estonian broadcast news. So actually this inspired this method because Estonian public broadcasting has an archive which contains news program recordings like this, and it has metadata that has all the speakers in this news program hand annotated. Of course, it doesn't have time information, but it has pretty good quality annotation for all the speakers that occur in this news recording. So can we use this information to train a speaker recognition model for public figures like politicians who often occur in news? So as training data, we used over 6,000 radio news shows from over 12 years. The data contains over 13,000 unique persons, but of course most of them occur only once. Actually, about 5,000 occur more than once, and for example, 1,500 occur more than 5 or more times. So we use this as training data, and as development and test data we used 16 shows from the same news program, but from a later period, to be totally fair. So it's quite realistic, I guess. So this was hand annotated. And the task is an open set speaker ID task. Basically, the task is to discover those speakers in those unseen news shows. A baseline model is a supervised I-vector-based speaker ID system trained on about 200 hours of manually transcribed data. So manually transcribed data with manually assigned speaker IDs and time segments and so on. And this training data has 800 speakers, which covers only about 28% of the speakers in the development set. The weakly supervised system has, on the other hand, almost 5,000 speakers, so all the speakers that occurred more than once, which covers almost 60% of the speakers. And both systems use I-vector plus LDA, PLDA-based speaker recognition approach. And the speaker identification models were tuned so that we have at least 95% precision, and this is the recall on development and test data. So we see that the supervised system gives us 15% recall, and the proposed weakly supervised system 41% or 45% recall. And we also analyzed how many times a speaker needs to have occurred in the training data in order for him or her to be recognized with good confidence. And it turns out that if the speaker occurred 5 or less times, then those speakers were never identified correctly. But for speakers occurring around 15 times or more, then those speakers were identified almost always. Well, there are some outliers, but still. Okay, so this was about speaker recognition. Let's move now on to language recognition. So spoken language recognition is an important subtask in many multimedia applications. The problem is that there are no large-scale free datasets for training spoken language recognition models that perform well on various kinds of speech from the wild. So there is a Mozilla Common Voice and VoxForge datasets which contain speech from different languages, but they all contain dictated speech, which is not really very optimal for various practical tasks. Another case is with conversational telephone speech. So then popular spoken language recognition benchmark is the NIST LRE evaluation, for example, the LRE 07 evaluation. And in order to train models for this evaluation, you are expected to use data from the Linguistic Data Consortium that actually costs over $15,000 for LDC non-members. So we asked the question, can we use YouTube as the data source for language recognition as we used it for speaker recognition? The problem is that most of the videos on YouTube do not have language information, so we cannot simply check what is the language of the YouTube video. So how to do it? we experimented with the following approach. We used Wikipedia corpus of a particular language to sample random trigram search phrases, and we used those random phrases to search YouTube, so retrieve videos from YouTube. So here are some of the sample search phrases. And the expectation is that at least some part of the videos that are retrieved as a result of such search phrases contain speech in this particular language. Of course, there are many false positives, and that's why we used many filtering steps to filter out videos that are probably not in this given language. For example, we applied written language identification model to filter out videos whose title or description are not in the expected language. We used student volunteers, international student volunteers, to verify a random subset of the data to whether they are really in this expected language. And it turns out that after this many of those filtering steps, 85% of the speech segments were really in this expected language. So, which gives us basically 15% of noise, which is not very optimal. So that's why you used another filtering step, data-driven generative classifier, to filter out outliers, which finally gave us 98% quality. So 98% of the utterances are really in the expected language. And this dataset is released publicly under the name VoxLingua 107 because it contains data from 107 languages. The total number of hours is 6,600. So this is the statistics per language. We see that there are, well, Czech language has 67 hours. Slovak, for example, has 40 hours. So 62 hours per language on the average. So how good models do we get from this data? So the first experiment considered in-domain data. So this VoxLingua 107 comes with a development set containing 1,700 utterances for which the language is verified by 2 independent persons to really be in this language. So we trained this language identification model on this VoxLingua 107 training data that uses this ECAPA DDNN model that is also popular nowadays for speaker recognition. We used cross-entropy training, and we got 6.7% error rate on this development set. The training recipe is published in the Speech Brain Toolkit, and the model is available in the Hugging Face repository. And the most common errors, as we see here, are errors that a human person would also likely make. We also experimented with this model on this NIST LRE 07 data, because luckily this VoxLingua dataset contains all the languages that are target languages in this NIST LRE 07 evaluation. Although our data is not conversational telephone speech, we still do pretty good on this LRE 07 data. So here we have a bunch of baseline results, which are all trained on in-domain data. So NIST, LDC data, LDC telephone speech data.
Is this the CRH or as the NIST official metric, or is it some equal error rate?
This is the official metric,
Okay.
yes. So I think this one is was the state of the art 2 or 3 years ago when we did this experiment. I think 2 years ago. I think now it has been surpassed by WAV2VEC or something like this. But we still are not far from the state of the art, although we do not use any in-domain data. Voxlingua 107 based embeddings can be also used for unseen languages and dialects. If a small labeled training set is available, and I think this is actually even a more practical use case of this Voxlingua 107 dataset, because it is not very difficult to collect a small dataset for each of your target languages. It's just difficult to do it on a large scale. So this slide describes results on the Oriental Language Recognition Challenge 2020. And task 1 is a closed set identification task for 6 languages, and task 2 is a dialect identification task. So considering 3 Chinese dialects and 3 interfering languages. And the training data is about, so the in-domain training data is 10 hours of data per language and dialect. So, so the first row in both of those tables is a result where you train your embeddings only on this in-domain data, and the equal error rates are pretty high. If we use the embeddings trained on Voxlingua, we get a very nice improvement, and the improvement is even better if we fine-tune the Voxlingua embeddings on this in-domain data. So we get very nice improvements. By the way, the official rules of this OLR challenge forbid using any external data, so that's why we don't claim that those are state-of-the-art results. We just show that Voxlingua 107 based embeddings can improve the results in such practical scenario. Okay? Finally, we can also visualize the language embeddings. Can you read this actually? Okay. So we can average the language embeddings over the training data and project them into this 2D space using this TSNE projection. And we get this very nice picture when we see that it reflects the true hierarchy of language families quite accurately. For example, this reddish group contains all the Slavic languages, the blue-green group contains the Finno-Ugric languages, and the yellowish area contains the Afro-Asiatic languages. So, of course, there are some obvious deviations. For some reason, we have the Scots language here, but we later learned that the Scots language Wikipedia has really, really bad quality, and also the Scots language had very little amount of training data from YouTube. So probably this Scots language embeddings are total crap. Okay, so basically this concludes my talk. Thank you for your attention. Just to mention that we are looking for PhD students and postdocs in our research group. Write to me if you are interested. Thank you.
Any questions actually from the people here? And we also have the YouTube chat where I can voice the questions. Any question here, guys?
Question.
Yeah, one microphone. Okay.
did you measure how the speaker embeddings are depending, the quality depending on the diarization? Because it's the first step and diarization can spoil everything, right?
No, we didn't measure it, but just to give you some background, we need to have some speaker diarization system in order to produce this in order to do this initial step. And actually, when doing this training for Voxel App, we used a speaker diarization system trained on Estonian data. So that shows that it's not very sensitive to the quality of the speaker diarization system. It was actually a GMM-based speaker diarization system.
And second one, did you attend the last Voxel App because it was for unsupervised data, which exactly match your scenario?
No.
Running this year.
I didn't, but I think it wasn't really exact match because it didn't have the speaker labels. It only had.
Yes.
But we need, in my method, I need to have the set of speakers.
Okay, so it's the diarization.
Yeah.
Okay.
I have actually one more question. You said that in this task where you finally train the embeddings or the system for the known speakers, then you have an extra one for all the unknown speakers.
Yes.
So actually this embedding, probably if you look at it from the distribution point of view, is very broad because it's fed by many voices. So does this cause any problem for you in, for example, the calibration or in the scores that this embedding is going to give contrary to the normal ones, or is everything fine?
We didn't analyze this this question in much detail. We noticed some other interesting things. For example, there seems to be that there are kind of some certain proto-speakers that tend to absorb a lot of unknown speakers, and for some reason one of them is currently the Prime Minister of Estonia. So it happens that a lot of so this which is Kaja Kallas, which is a female person. So when we apply this model on unseen data, then this Kaja Kallas is detected much more than is expected.
Maybe a good qualification. Yes. to become a prime minister. So.
Yes, we don't know.
Anything else, guys?
Maybe one more question about this language ID corpus. You said that you obtained something like 98% pure data. So this was verified by having some random subset verified by some auditors?
Yes, we used basically international students of our university who know those languages. So it's a very ununiform distribution.
Okay, so it's not for all of the languages?
No.
Okay.
And also we noticed that this purity is very different for different languages. For some languages you get very good quality, and I think it was so that those languages which have their own writing system, like Georgian, they have their own alphabet, then you get very good quality. But for other languages that share the writing system with other languages like, I don't know, Czech, Slovak, Estonian, there you get a lot of, well, you just get, typically you get English data as response to Estonian or Czech queries.
Okay. Thank you.
I'm not going to throw the microphone, so just be loud.
I will repeat the question.
Yeah.
Perfect. So with the speaker ID thing, or the speaker segmentation thing, when you do the segmentation, what do you do with the unknown class? Do you discard it, or do you
Yes. So the question was that when we do the training data relabeling with a trained model, what do we do with the unknown speaker? And the answer is that yes, we just discard it. We don't give it any label, and we throw it away from the data set.
So basically, those segments you assign to a different speaker. The segments of the system labels as this unknown speaker. Do you label them as the next best speaker, or do you just throw them away completely?
If I understand the question correctly, then yes, we throw them away. We don't do anything special.
Okay, but then in the initial training phase, you have this scale divergence between the prior, like some prior probabilities. Essentially, I'm thinking if you have multiple turns for a single speaker, then almost necessarily you would discard the second turn, right?
Second turn. So okay. After we do the diarization, we also average the embeddings for overall turns of a single speaker cluster. So basically, this gives us only one embedding for each discovered speaker cluster.
Overall utterances.
So for example, here we have speaker A, and we get only one embedding for speaker A.
And so actually, maybe in this picture right now, you would say that you have 1, 2, 3, 4, 5, and so you want the KL divergence to be 1 over 5, 1 over 5, 1 over 5. Right?
No, the KL divergence is done over the embeddings averaged over the clusters. So here I have 5 segments, but I only have 3 embeddings. Okay?
The average is done from each utterance, right? Or averaging all the audience? I mean, average of embeddings.
Yes.
The average is done per utterance.
Averaging is done over all the utterances of a single cluster.
So basically, I also wanted to ask you about this averaging. Are you somehow conditioning the length of the segments into an embedding to go into the averaging? So for example, if you have some spurious detection of some speaker A that is just quarter a second, do you take it into the averaging or you discard it?
No, we don't do any such, we do nothing, we just average.
Okay.
But it's a good idea to consider something.
Maybe actually Anya then would have some advices there with the distributions rather than point embeddings, but this is maybe for offline discussion. I'm just telling your work.
The probabilistic embeddings, I think I know their work. Yes.
Yeah. Hello. Yeah. So the diarization system you said was on Estonian data. Was it like you have speaker labels when you train this system, or it was completely unsupervised somehow?
Unsupervised, classical way.
Unsupervised. So actually, your whole pipeline is unsupervised in this sense.
Yes.
Okay.
Yes.
Thanks. Yeah, that was all.
Okay, so if there is two more questions? Okay, if no questions, I think that's it. Thanks a lot, Tanel, for his talk, and he will be around for the rest of the week, so actually I think more deep discussions can follow. Thanks a lot, Student Union and our colleague here for technical support, and that's it. Thanks all of you for being here.